Hi. Today we're going to continue our talk about numbers in polar form, only this time we're going to take a look at complex numbers in polar form. And you will remember that a complex number has this format: some real number part plus an imaginary part, so a plus bi. Complex numbers can be graphed in the complex plane, which is defined as having the horizontal axis as the real number part and the vertical axis as the imaginary part. So if I were to plot, I'm going to call these A, B, C, and D. I'll go ahead and plot the first one and then ask you to plot the other numbers. Point A is 2 in the real direction. You could think about this: the A goes here and the I goes here. 2 in the real number direction, but 3 in the imaginary direction. So there's point A right there. Go ahead and plot point B. Yep, that's what I thought. 3 negative and 5 negative. This one, Z, is just -4. No imaginary part to this one. So there's C, and if Z is -I, that's -1I. So there's our fourth point. Very good. The absolute value of the complex number, absolute value of Z. If you think about that, folks, I want to just sketch in one little triangle here and ask you to think about that. That was 2 in the real direction and 3 in the imaginary direction. And to find the absolute value, that's the distance that that number is from the origin, that's a Pythagorean theorem thing. The absolute value of Z is going to be the square root of its A squared plus its B squared. Again, that represents the distance from the point to the origin, or vice versa. And we're asked to find the absolute value of this complex number. So the absolute value of that first one is going to be the square root of, you take its A and its B, 5 squared plus 12 squared, or some of you may already have been there. That's the Pythagorean triple, 13. So the absolute value of Z would be 13, or the distance from this point to the origin, 13. Take a quick look at this one, the absolute value of this complex number, square root of 2 squared plus -3 squared, that's 9 and 4, square root of 13 for that one. So let's see how we can relate this in the polar form, because that's the goal of this lesson, is to do arithmetic with complex numbers in polar form. So we have a diagram here for you that shows a polar number graphed. The coordinates are A and B because the number is A plus BI. And as we said a moment ago, the square of R is equal to the square of A plus B, right? A squared plus B squared. Think about the cosine of the angle theta here, and I'm going to just jot that down here. The cosine of theta, well, that would be its adjacent side A over R. So if we solve that for A, then A is equal to R times the cosine of theta, and I hope that sounds familiar to you, because we've seen that before. Remember that cosine goes with the x value. Likewise, based on the sine ratio, so you could do the same thing here. The sine of theta is equal to the opposite side B over R, so R sine theta would give you a value for B. We should also point out, since we're talking about conversion formulas here, that you can find theta. So there's not a spot for this on your notes page, so please add it up here. You can find theta by taking the tangent inverse of B over A. And a reminder that you'll have to look at the signs SIGN on points before you decide where that theta is, okay? Because you may have to add pi radians to it if it's in the second or third quadrant. So with all that said, the polar form of a complex number, z equals, and in polar form it's r times the cosine of theta plus I times the sine of theta. Okay? R times the cosine of theta plus I sine theta. Some people call that R cosi. I've heard it called that before. R is called the modulus of the complex number, and theta is called the theta part. It's called the argument of the complex number, where theta is between 0 and 2 pi. Okay, our first task is to write this number, this complex number, in polar form. So we need to know what r is. And we know, based on what we've done so far, that r is the square root of a squared plus b squared. And that works out to be the square root of, well, it's 1 plus 3, square root of 4, so r is 2 here. To find theta, we can do the tangent inverse of its negative root 3 over negative 1. Folks, this is in quadrant 3. That is the tangent inverse of just root 3. And looking back at what you already know, or using your trig reference table, the angle whose tangent is square root of 3 is pi thirds. But folks, remember, tangent, this is saying that the angle in the first quadrant, whose tangent is this, is pi thirds. And we need to be in the third quadrant, so we have to add pi to that real quickly. If we want to go from pi over 1 and make it some number of pi thirds, it would have to be 3 pi thirds, right? Multiply the bottom by 3, multiply the top by 3. So we're going to add 3 pi thirds here so that we get this angle into the quadrant where it belongs, which is the third quadrant. So that's 4 pi thirds. Now to write the number in polar form, z would equal, and it will be the radius, I'm following this format, times the cosine of 4 pi thirds plus I times the sine of 4 pi thirds. And there you have it. We got it written in polar form. Now we're going to go the opposite direction and write this in rectangular form. So our answer should be in the format a plus bi. And let's see. To get a, we need r times the cosine of the angle. So I'll write the formula, but that for us is going to be 4 times the cosine of 30. And from your unit circle or your trig reference sheet, the cosine of 30 is root 3 over 2. So we're talking 4 times root 3 over 2, which is, let's see, that cancels, so 2 root 3 if I'm thinking correctly. Then to find b, that is r times the sine of theta. And in our case, r is 4, and the sine of 30, again, you get from your trig reference sheet, 4 times 1/2 it is. So that's 2. So in rectangular form, our number is going to be this. Z is 2 times the square root of 3 plus 2i. And there we are in rectangular form. So our conversion equations are here. R equals, so we had r squared up here, but what we used was r, and I know that you guys can make that distinction, but I'm going to write it here anyway. R is equal to a squared plus b squared. Theta is the tangent inverse of b over a. A is r cosine theta, and b is r sine theta. Those are the things that we need to be successful at doing arithmetic with complex numbers in polar form. All right. Now, what I would love to have you think about is if we can, we could certainly add and subtract complex numbers. That's easy to do. Multiplying them, if you recall, if you're going to multiply, so I'm going to put a what if out here. If I'm going to multiply some a plus bi times another, who knows, c minus di, folks, that's a FOIL thing or a box method thing. Working with those complex numbers in polar form is much easier to do multiplying and dividing without all the hassle of FOIL or the box method. And I want to give you a rule, and then we'll talk about what that means in words, and we'll do it here. It says if you have one complex number in polar form and another in their product, that is, when you multiply them, this is what you get. Z1, Z2 is equal to, it's R1 times R2, so modulus 1 times modulus 2, and then it is the cosine of, when you're multiplying, it's the sum of the angles, so theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. You multiply the moduli, you add the arguments. Okay, so if we're going to do that here, to multiply these two numbers together, our product will be, well, it's 6 times 5, and all of that multiplies the cosine of, it's the sum of the angles, so 40 plus 20 plus I times the sine of 40 plus 20. So there's my substitution step, but it works out this way. 6 times 5 is 30. The cosine of 60 plus I times the sine of 60. And there's our product. Really much quicker than doing the box method or doing FOIL. It's true, sad but true. FOIL's fast, but this is faster. So if we can get good at this, we'll be real speedy. Dividing, as you might imagine, does the opposite operations. Instead of multiplying the moduli, you divide them. So you would have R1 divided by R2 times, and it's the cosine of, not the sum of the angles this time, the difference. So it should be theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. You divide the moduli and subtract the arguments. Alright, if we're going to divide here, then our new number, Z1 over Z2, is going to equal, and it's 50 divided by 5, so I'm going to just cut to the end here, that's 10, times the cosine of, and we subtract the angles, 4 pi thirds minus pi thirds, 4 pi thirds minus pi thirds, that's 3 pi thirds. You guys, that's the same thing as pi. So it's the cosine of pi plus I times the sine of pi. And when we divide those two numbers, that's our quotient. All right, the next little bit we're going to talk about exponentials with complex numbers in polar form, but really, folks, exponentials are repeated multiplications, so it uses what we already know. This is called De Moivre's theorem, at least I think that's how you say it. I have a terrible French accent, but I think it's De Moivre. I'm not sure. Anyway, he is the one who came up with this idea that if we raise a complex number to a power in the polar plane, we can shortcut by saying this is the number that we want to raise to. So it's modulus to that power, r to the n, times the cosine of, and then it is exponent times theta plus I times the sine of exponent times theta. So you raise the modulus to the nth power and then multiply the angle times the exponent, or angle times power. All right, let's try that here. We're going to raise this complex number to the 5th power. So our number to the fifth will be, it's 2 to the fifth. 2 to the fifth is, let's see, 2, 4, 8, 16, 32. So it's 32, 2 to the fifth, times the cosine of, and then it's multiply exponent times angle, 150 plus I times the sine of 150. And there you have it. We've raised that complex number to a fifth power with relatively, that's kind of painless, really. Not bad. And if you think about the fact that finding the nth root of some number is equivalent to raising it to the 1 over n power, we can find the principal root of these complex numbers pretty quickly. There is a good demonstration of how you find all of the roots of the number, but we're going to just go for the principal root, that is the first one that you find. So we're going to find the fourth root of, so we're going z to the fourth power, 1/4 power. We take the modulus, 16, and raise it to the 1/4, and then it's the cosine of the angle times 1/4, right? Because that's what the multiplier is, the exponent. So we're 1/4 times 60 plus I sine that same thing, 1/4 of 60. And then doing the work, the fourth root of 16 is 2, and 1/4 of 60 is 15 degrees. So it is 2 cosine 15 plus I sine 15, and those are both degrees. They should be marked that way. All right, there you have it. We've done some arithmetic with complex numbers in polar form. Get out there, try that U-try quickly as you can.